Hi everyone, good evening. How are you all? It's really great to have all these people waiting in the queue for this amazing session to get started. I can already see a lot of comments in the chat, and trust me, I too am very excited for this session because obviously reading its title gives us so many expectations and hopes. So, to guide us through the whole process and answer a lot of our questions, we have with us a very eminent speaker, Mr. Saurabh. Hi, Saurabh.
Hey Dhwani, hey everyone.
How are you?
I'm good, I'm good.
Saurabh, it's really an honor and privilege to have you here. Thank you so much for joining us. And I really look forward to this session and all the information that you have to give to us. I can't wait to take it all. So at this point, I would really like to invite you to kindly introduce yourself.
Yeah. Hello everyone, this is Saurabh Gupta. So I'm currently working as a software engineer at Cred. So there I basically work in the backend team, which involves building large scale distributed systems, microservices and all. Apart from this, my usual job, I work as a I work as a mentor at Geeks4Geeks. So I've been working at Geeks4Geeks for the mentor for the course, which helps working professionals to get polish their skills and data structures and algorithms and get them prepared for their interviews and all. So yeah, I'll be the instructor for that particular class. Yeah, that's pretty much. So before working at Cred, I've been worked to companies like Urban Company, Direct Eye, Take On Corp, etc. Right? Yeah, that's pretty much about me.
That's amazing. So, sort of without taking much of your time, I would like to request you to kindly present your screen and tell us all about what this course is all about, how it will help us, like the students, because I personally am a student and I can't wait to get all the deets out of it. So,
Yeah,
let's just go ahead with it.
sure, sure. So I'll try to share my screen.
Sure.
So yeah, firstly I'll take you. I hope you all can see my screen. I just want to know in the chat if you all can see my screen. Oh yeah, I guess it should be with Dhwani. Can you tell it's visible, right?
Yes, I can see your screen.
Yep. So I'll just firstly take you through. So what we are going to discuss today is firstly take you through the course that will be there for like from Geeks for Geeks, like that is starting in the next week, and I'll be the mentor for that particular course. And what is going to be the structure? What is going to be the structure of that course? What all things we are going to discuss in that course briefly, and then today I'll be discussing a very small topic with you all that is called topological sort. So yeah, in very brief I'll discussing one of the topics, so that will give you a gist about how we discuss things in this particular course, right? So I'll just take you through the course. Yeah, so if you'll go to the Geeks for Geeks live courses and select this DSA for working professionals, so you can explore this course. Okay, so what this course has to offer you? So this course is a kind of a 2 months course. Okay, so there'll be total of 16 classes. And each of the class will be taken by me only. So we'll start with the very basic things in data structures and algorithms. So like you can see the whole week's like content what we are going to discuss. In week 1 we are going to discuss the analysis of algorithm and arrays. In the week 2 we are going to discuss bit manipulation and hashing. In week 3 we are going to discuss strings. And so you can see, right, we'll be starting from very basics. So if you know if you're someone who know very basics into coding, you know how to write a loop, how to write if else statement, then this course is for you, right? Will help you start from very basics and will take you to the advanced topics such as graph, greedy algorithms, dynamic programming, heaps, and everything, right? So yeah, so if you know basics of programming, so that this course is going to be super helpful for you. So when this course, who's the course instructor? So no guesses here. So I'll be the one who will be teaching the all of these topics in this particular course. Yeah. Now, when is the batch starting? So batch is batch name is GCL46. It is starting from 23rd of July, and the timings of batch would be 2 p.m. So every class would be a 3-hour class. So you can log in to Geeks for Geeks, and you can register at this particular page. So that you can be part of this amazing course, which will help you polish your data structure and algorithms and get you prepared for the interviews, right? So yeah, that's pretty much about this course. Now I'll quickly jump into the thing that I promised, that today I'll be discussing with you all a small topic that is called a topological sort. So which will give you a hint about how do we teach, what is our teaching methodology that we opt for in this particular course, and yeah, everything around that we'll be discussing. So yeah. So before that, I'll just quickly jump and see if there are some comments. So if you want to comment anything, if you want to say anything, just put it into the chat. In the end, I'll just go to the chats and all, and I'll try to answer some of your questions. Right?
Hi, Saurabh. Sorry to interrupt you. I just wanted to let the audience know that I have pasted the link of this course in the chat, and you can all, and it's also showing up on the screen. So you can just directly navigate to the course and, like, enroll in it. And there is a form in the chat also. You can also fill that one up. So go ahead.
Sure. So, with that, let's start with today's topic that I'm going to discuss. So, before starting with the topological sort, so I will need some of the basic prerequisites for this particular topic, so that you can understand this particular topic. So, it's just for this topic we are going with this prerequisite. So it's not that in the like in the class I'll start directly from graphs and all, but I wanted to teach topological sort that requires this particular prerequisites. So just be patient and hold with me. Yeah. So the prerequisite, that is, one, you should know the basic terminologies of graph. What are vertices, what are edges, and what is a directed graph, what is the undirected graph, etc. So if you know such things, so you'll be able to understand easily what is the topological sort. Secondly, you should be able to understand what is the in degree, out degree, or a degree of a graph, of a vertex in a graph. So that'll help you out in understanding the topological sort better. The third requirement for this particular topic is that you should know what are queues. Okay, so queue is nothing, it's a simple linear data structure which follows FIFO fashion, like of inserting and removing elements from it, right? So yeah, these are the prerequisites of starting the topological sort. Okay, so without wasting any time, let me just quickly jump into. Okay, before jumping into the topic, I'm again repeating that if you have any questions, if you want to ask anything related to course, related to anything around this. GCL course, geeks classes, so you can ask in the chat. I'll try to go through the questions at the end of the session, and I'll try to answer some of those, right? Okay, let's move on to our topic, topological sort. So what is topological sort? So if you'll go by the definition, so topological sort, okay, this is there's a spelling mistake here, I'll just correct it quickly. It should be linear. Yeah. So what is a topological sort? So topological sort, if you go by the definition, it is a linear ordering of vertices. So what are vertices? So if you know graph, right? So every entity, the data storing entity, where you, so in very simple terms, data storage entity is called the vertex in a graph, right? So topological sort is a linear ordering of the vertices such that if there is an edge from u to v, right? If there is a directed edge from u to v, so u should always appear before v in that linear order, right? So this is what is called topological sort. So I'll again repeat, what is topological sort? It is a linear ordering of vertices in a graph such that if there is a directed edge from u to v, then u should always appear before v, and this should be true for each and every edge into this particular given graph. Okay, for example, these are two given graph. I'll take these examples, so I'll just quickly remove that. Okay, so what could be the so if let's take an example of this first graph, right? What could be the one possible topological sort for this particular graph? So it could be, so I'll just write and I'll explain why it is a topological sort. It could be a B, and C. And it could also be A, C, and B. Okay, there are two possible topological sort for this particular given graph, given directed graph. Okay, why these both of these are topological sort? So if you'll pick up this particular edge which is from A to B, right? So it is starting from A and it is going to B. So what I said, if there is a directed edge from U to V, so U should always come before V, right? So A is, there is a directed edge from A to B, so A is coming just before B. So this particular edge is like this particular condition is satisfying this particular order. Similarly, in the second topological sort order also, A is appearing before B. So then the condition is not violating for the topological sort for this particular edge in both of these sorting orders, right? Now in the second edge, okay, if you'll see the second edge, there is a directed edge from A to C, right? Now if there is a directed edge from A to C, then A should, according to the definition, A should always come before C. Okay. And if you'll see in the first ordering, first topological sort, A is coming before C. Okay. So A is coming before C. So you can see in the first order itself, A is coming before C. Similarly, you can see, right, in the second order itself, sorry, in the second linear order itself, A is coming before C. Okay, so this particular ordering is also satisfying the satisfying the this particular condition, right? Okay. Now I suppose this particular thing is clear. Now let's take let's take an example of a more complex graph. So this, let's take this second graph, in which you can see there are multiple edges. There are 1 2 3 4 5 edges, sorry, 5 vertices, and the number of edges are 1 2 3 4 5 also, right? The number of edges is also 5, the number of vertices is also 5, right? Now let's try to write one possible topological sort. Okay, so one possible topological sort for this would be A, C, D, A, C, D, B, and E. Okay, now let's try to verify whether this particular topological sort is true, correct or not, right? So uh, let's take example of this particular edge, right? There is a directed edge from A to C. So if there is a directed edge from A to C, then A should come always before C. And you can see A is coming before C. That is correct. Now let's, so this particular edge for this, the condition is true. Now let's come to this particular edge. For this particular edge, for this particular edge, there is a directed edge from C to D. Okay, so C should come before D. Okay, so, and you can see that C is coming before D. So for this particular edge, the condition is holding true, right? Now if I'll go to this particular edge, you can see there is a directed edge from A to D. So I can see the directed, if there is a directed edge from A to D, then there should be a, so A should always come before D. Okay, so you can see that A is coming before D, right? So for this particular edge also, the condition is true. Now there is a directed edge from B to C. Okay, that means B to D. So it means that B should always come before D. And okay, sorry, this is a wrong topological sort that I've written. I just realized. So it could be DB. Yeah, my mistake. B and D. Right. So now this looks fine. Yeah. So if there is a directed edge from B to D, then B should always come before D. And you can see in this particular sort, B is coming before D. Okay. So for this particular edge also, the condition holds true. Similarly, moving forward, in the next edge, which is from B to E, okay, there is a directed edge from B to E. So B should always come before E. And you can see in the ordering that B is coming before E. Okay, so you can see for all the edges, the particular condition which is there for topological sort, it is holding true. So we can say that this linear ordering of the vertices is a topological sort. Similarly, this is one topological sort. There could be many more topological sort. Okay, one could be B, A, C, D, E. This is also one possible topological sort. Another possible topological sort could be A, B, C, D, E. So you can see that for a given particular graph, there could be more than one topological sorts that can be happen, right? So I suppose this is clear to everyone. Now I'll move on to the next thing, that is topological sort is applicable to which kind of graph. Okay, so like the first question that comes, is topological sort applicable on all kinds of graph? The answer is no. Then what kind of graphs the topological, for what kind of graph the topological sort is applicable? So that is only one specific kind of graph, that is called directed acyclic graph. And I'll tell you why it is only applicable to directed acyclic graph. So first let's take why it is not applicable to undirected graph, and why it is only applicable to directed graphs. Okay, so let's say if there is a undirected edge between A and B. So let's say there is a graph in which two nodes are there, two vertices are there, A and B, and there is an undirected edge between them, right? Now, if there is an undirected edge between them, then can you tell whether A should come before B or B should come before A? You cannot say that, right? So what was the condition of topological sort? If there is a directed edge, then it should happen from U to V, there is an edge, then U should come before V. But in an undirected edge, you cannot determine whether A should come before B or B should come before A. So that is why it is only applicable to a directed graph. Okay, in undirected graph, it is not clear whether which particular vertex will come before which the other particular vertex, right? Okay, now the thing is clear that it is only applicable to directed graph. Now coming to the second thing, which is acyclic graph. Okay, acyclic graph are the graph which does not contain any cycle or loop. Okay, what is meant by cycle or loop, that you should already study as part of graph. Okay, so currently I'm assuming that you know what is acyclic and what is cyclic graphs. Okay, but if you don't know, you should join the course, and then we'll discuss in detail. So why it is applicable to acyclic graph only? So let's say there is a graph, directed graph, A to B to okay, C. So there is an edge from A to B, and there is an edge from B to C, and there's an edge from C to A. So you can see that this is a directed graph, but this graph contains a cycle. Why does it contain a cycle? Because if I'll start from A, I'll go to B, and from B I can go to C, and from C I can come back to A, right? So I can come back to the same particular vertex following some path. Okay, so that is why this particular graph is a cyclic graph. Okay, now if we try to write down the topological sort for this particular graph, we won't be able to write. Why? Let's try it. So for this particular edge, okay, so A is, there is a directed edge from A to B. Okay, so A should always come before B. So I will write A, B. So where A is coming before B. Now from B to C, there is a directed edge. So according to the topological sort definition, B should come before C. So I will write A, B, C. So B will come before C. Okay, that is okay. Now I've written that. Now coming to the third edge. Okay, there is a directed edge from C to A, so that C should come before A. But you can see in a linear order, it is not possible for C to go come before A, because C is supposed to come after B and B is supposed to come after A. So it cannot be possible if in a linear fashion it is not possible that C can come before A. So that is why topological sort is not applicable for cyclic graphs. Okay, that is why topological sort is only applicable to directed acyclic graphs. I suppose that is clear to everyone. Okay, if that is clear, I will move on to the next thing of how to write an algorithm to solve this particular problem of writing a topological sort of a directed acyclic graph, right? Now, in order to understand the algorithm or develop an intuition, we need to understand what are the n degrees of a graph. Okay, so let's take the example of a similar graph that we have already seen. Okay, this is 1 2 3 4 and 5. Okay, so there is a directed edge from 1 to 3. There's a directed edge from 1 to 4. There's a directed edge from 2 to 4. Okay, there's a directed edge from 3 to 4, and there is a directed edge from 2 to 5. Okay, now what is the n degree of a vertex in a graph? The n degree of a vertex in a graph is the number of incoming nodes onto that particular vertex. Okay, the n degree of a particular vertex in a directed graph is equal to the number of incoming nodes on that particular vertex. Okay, so let's try to calculate the n degree of all the nodes here, right? So the n degree of this particular node, sorry, vertex, the first vertex is how many number of incoming nodes are there. So there are no incoming nodes here, right? So the n degree is 0 because there are no incoming nodes on this one. Okay, now let's try to calculate the n degree of this vertex with a number equal to 2, right? So are there any incoming nodes on this particular vertex? No, there are no incoming edges on this particular vertex, so the n degree of this particular vertex is also 0. Now let's try to calculate the n degree of this vertex, right? How many incoming edges you can see on this particular 3? It is equal to 1. Okay, because this is an incoming edge, right? We're not talking about outgoing edges, so the incoming edge is only 1. Okay, and the other one is outgoing edges. Yeah, now let's talk about this 4. Okay, what is the n degree of 4? So the number of incoming edges is this one and this one. The total 3 edges are incoming to uh, this particular vertex, right? Now what about this particular vertex? The number of incoming edge is 1, so the n degree of this particular vertex is also 1, right? So this is how we calculate the n degrees of vertices, right? Vertices in a graph. Now let's talk about the intuition of the algorithm, right? So what we are trying to do in this algorithm is, it is kind of we are trying to order things in such a way that, let's say if 5 has a dependency on 2, okay, we'll call this edge as a dependency. Okay, I'm saying 5 has a dependency on 2. Okay, so if we see all the edges as a dependency, right? So the first one that should run, that we should write in a topological sort is the one which does not have any dependency. Okay, the first vertex into our topological sort should be the one which does not have any dependency, because I cannot write 5 directly because it has a dependency on 2, so 2 should come before 5. I cannot write 4 because 4 has a dependency on 3, 1 and 2. I cannot write 4 directly, right? So I should find a vertex which does not have any dependency. So again, I'm saying what I'm referring by dependency is an incoming edge is a dependency, right? So then we need to find the vertices which does not have any dependency, or in very simple terms we can say which does not have any incoming edges. And in more simple terms we can say that we need to find vertices whose in degree is equal to 0, and that will be the one which will come first in the this algorithm, sorry, in topological sort. Okay, so if we can see what are the what are the indices, what are the vertices which are having 0 in degrees. So these are 1 and 2. Okay, because they do not have any incoming edge, so they have 0 in degrees and they do not have any dependency, right? So this will be, we can write them directly, doesn't matter, right? So while I'm writing one, so I'm resolving this particular dependency. That means one has already been put into the order. All those who are dependent only on one, they can be written now after this particular, once the one has been written, right? So what are the dependents on one? So the dependents on one are 3 and 4, right? So once we have written one into this order, we can decrease the in degree of 3 and 4 by 1. So this is how we can, this is the intuition of the algorithm. This is not the whole algorithm that I've uh, explained. This is the basic intuition how you should try to approach this particular problem. Firstly, I am trying to order every vertex in the graph in such a manner that if there is an incoming edge from u to v, you should come before v. So I need to find that u which does not have any incoming edge. Okay, that means that does have in degree equal to 0, or that does not have any dependency, right? And we are going in that direction. Okay, I suppose this is fine to everyone. Now I'll quickly jump into the algorithm, right? So in, like, for today we are going to discuss only a bfs based so again, this particular topological sort can be done in a dfs based algorithm or bfs based algorithm. For the for the current session, I'll be taking help of the bfs based algorithm to explain it to you all. And yeah, let's jump on to the algorithm for this particular problem, right? Now what we will try to do is, the first step in the algorithm would be that I will try to calculate the n degree of each and every vertex in the graph. Okay, and you know what are n degrees, so I will calculate the n degree of each and every vertex initially, right? So the n degree of this zeroth no, zeroth vertex is 0 because it does not have any incoming edge. The n degree of this vertex is 0, again there is no incoming edge. The n degree of this particular vertex is 1 because there is one incoming edge on this 2. The in degree of this third vertex is 3 because there are 3 incoming edge on this particular 3. And the in degree for this 4, vertex 4, is 1 because there is only one incoming edge on this particular vertex, right? There's only one incoming edge, right? Now moving forward, now what is the next step? The next step is we should create a queue. Okay, how queue will help us, I'm going to tell you, right? We need to create a queue. Okay, and this should be a simple queue, FIFO queue. Okay, it need not to be a priority queue, anything else, right? Now once we have created a queue, what we will try to do in this algorithm is we will try to find out all the vertices which have in degree equal to 0. Okay, which have in degree equal to 0. Why we want to find all the vertices which have in degree equal to 0? Because they are not dependent on, they do not have any dependency. Okay, so there is no incoming edge on them, so it is not, there is no foundation that something should come before them. Okay, so we can find out those particular vertices and put them into this queue, and you can put those vertices in any order. There's no foundation that you should follow any order, because there could be multiple topological sorts for a particular given graph, directed acyclic graph. Okay, so currently in our given graph there are two vertices which have in degree equal to 0. Which are those? This zeroth vertex and this first vertex. Okay, so we will insert 0 comma 1 into our queue. Now what is the next step? Once we have done this, we will start iterating through a loop. So this loop will start iterating. Okay, and this loop will run until my queue is not empty. Okay, until if there is a one element or also, this particular loop will keep on running, right? Now once we get inside this loop, we try to pop out the first element from the queue, right? So what was the first element that was put inside the queue? That was the 0. So we pop out that element. So I'll just remove this particular element quickly. Okay, so this 0 is popped out and it is stored in U. Okay, now that means if that particular vertex is in the queue, that means it does not contain any dependency. It has a in degree of 0. So we can write it we can write that particular vertex in our topological sort. So what we will do, we will print U. Okay, you can, if you want, you can print U. You want to store into an array, you can store it into an array, whatever, do whatever you want. So currently I am printing the topological sort, so I will print. So I'll consider this as my output screen. So I will print 0. Okay, now once I have printed 0, that means this particular dependency has been resolved. That means this 0 has been resolved. Okay, anyone who is dependent on 0 is now free to, who is only dependent on 0 is now free to get into the order of the topological sort. Okay, now so in order to find what all nodes, what all vertices were dependent on this 0, we will try to find out all the adjacent vertices, all the adjacent node V of U, right? So all the adjacent vertices of U we will try to find out, and we'll call those vertices V. Okay, we'll try to iterate them one by one, right? So what is the first adjacent vertex of 0? That is this 2. Okay, for this 2, what I will do, because this 0 has been resolved, right? So I will decrease. So that means this particular edge has been resolved. So I will decrease the in degree of 2 by 1. So earlier the in degree of 2 was 1. Now it will become 0, right? So I will write 0. Okay, now what is the, so once I have decreased the dependency of this, I've decreased this dependency, and I have removed, sorry, I have removed this dependency, and the in degree of 0 of this 2 has become 0. Now once the in degree of a particular vertex becomes 0, it is now free to be included in the topological sort. So once I reduce the in degree by 1, I will check after the reduction, if the in degree of that particular vertex becomes 0, I will push that inside the queue. Okay, so I will push V inside the queue because it is ready to be included in the topological sort. So inside queue, after 1, 2 will come, right? Now moving forward, what is the next adjacent element, next adjacent vertex of 0? That is 3. Okay, and this particular dependency has also been resolved. Okay, so I will decrease the in degree of 3 by 1, right? Because I'll have to decrease. So the in degree of 3 will become, instead of 3, it will become 2. And after decreasing the in degree, I will check if the in degree of this particular adjacent vertex is becoming equal to 0 or not. It is not. Okay, so that is why I will not put 3 inside the queue. And why I'm not putting, because although one dependency on 3 has been resolved, but there are 2 more dependencies. So 3 is not free to get involved into the topological sort order currently, because it has more dependencies. Although one dependency has been resolved, but other dependencies are remaining. So that is what. So that is happened. Now this particular thing is over. Now I can come again. I will check the queue is not empty. Okay, the queue is not empty. So what I will do, I will pop out the next element, that is 1. Okay, so one is removed out of the queue. Okay, now one is removed of the queue, so one was there in the queue, so one is free to be printed in the topological sort order. So I will print one. Okay, because I'll have to print one, because one does not have any dependency now. So that dependency has been resolved, and I will put one in the topological sort. Now after I have put one into the topological sort order, I will try to see what are the dependents of one. That means what are the adjacent vertices of one. So the adjacent vertices of one are 3 and 4. Okay, now I'll go to them one by one. Okay, so the first adjacent vertex of one is 4. Okay, I can go to adjacent vertex in any order, right? There is no that I should go to 3 first and then I should go to 4 later, right? There is order is not mandatory, right? So now I'll go to 4. Okay, now for 4, this one dependency has been resolved. So what I'll try to do, I'll try to decrease the topology in degree of 4 by 1. So here you can see reduce the in degree of v. So that is 4 by 1. So once I reduce it, the in degree becomes 0 for 4. Now, sorry, it becomes 0. Now, once the in degree becomes 0, I will check if the in degree is 0. And if the in degree is 0, that means it is free to be included inside the, like in the topological sort order. So I will put this 4 in the queue. That means it is free to be included in the topological sort order. Right. Now, what is the next adjacent element of adjacent vertex of 1? That is 3. Okay. Now, 3 is I will decrease the in degree of 3 by 1. So it was 2 earlier. Now it will become 1. Okay. Now after like this particular dependency has also been resolved, but still 3 is not free to be included in the topological sort order because of one remaining dependency, that is this. Okay, because that dependency has not been resolved yet. So I will not put 3 inside the queue. Okay, because the in degree of 3 is not 0. Okay, so I will move forward. Okay, and I'll remove this one and I'll go to this while queue is not empty. Queue is not empty, so I will pop out the first element in the queue, that is 2. 2 will be popped out and 2 will be printed because it was free to be included in the topological sort order. Okay, now once 2 is printed, I will try to go through the adjacent vertices of 2. What is the adjacent vertex of 2? The adjacent vertex of 2 is 3. Okay, and the adjacent vertex of 2 is 3, so I will try to decrease the in degree of 3 by 1. It will become 0. Okay, and once it becomes 0, now 3 is free because all of its dependencies has been resolved and 3 can be included into the sort order. Okay, so 3 will be pushed inside the queue, 2 will be printed. I will go to the next element in the queue, that is 4. Okay, so 4 will be popped out. Okay, because now the queue is not empty yet and 4 will be printed. Now I will try to go to the adjacent elements, adjacent vertices of 4. So there are no adjacent vertices of 4, so there is nothing which I want to traverse in this particular for loop, right? So this is okay, right? Now I'll go to the next element. Now I'll again check the queue, it is not empty. Okay, now I will pop the next element inside the queue, which is 3. 3 will be popped out and 3 will be printed. So there is no dependent, like now I'll try to check, are there any adjacent vertices of 3? No, there are no adjacent vertices of 3 though. So this particular loop will not run for 3 and I don't need to do anything here. Okay, so 3 will be removed, as 3 will be printed and removed from the queue. Now in the next iteration, I can see that my queue is empty. So this while condition would be false and I'll come out of this while loop. Okay, and the sort order would be 0, 1, 2, 4, 3. Right? So this is the topological sort which we have got from applying this particular algorithm. Right? There could be more possible topological sort, but this is one such topological sort for the given directed acyclic graph. Right? I assume this is clear to everyone. Okay. So this was a very simple algorithm to find a topological sort of a directed acyclic graph. and this was a BFS based algorithm, right? You can do this particular algorithm. So you can write the topological sort using a DFS based approach also, that we will be discussing in detail in the course, right? Again, one more thing, this particular BFS based approach is also called Kahn's BFS based sorting algorithm, right? There are multiple applications of this particular algorithm. This particular algorithm is used to detect cycles in a graph, if there is a cycle or not. You can use this algorithm. How? That we'll discuss when we discuss this topic in detail in the course, right? uh, uh, like there are multiple applications which you can use, which for this particular algorithm can be used. Okay, I suppose this is clear to everyone. Now, coming to the complexity analysis of this particular algorithm. So, what is the space complexity? So, it's clearly visible that we are using an extra queue. Okay. Plus, we will be using some array or list to store the in degree of each of the vertex, right? So, this will contribute towards the auxiliary space complexity of the particular algorithm, right? So clearly the space complexity is O of V, capital V, where V represents the number of vertices in the graph. Now let's try to think about the time complexity, right? What is the time complexity of this particular algorithm? So now let's try to, time complexity is slightly tricky to understand, but I guess it will be easily getting it. So first of all, this outer loop is running for every vertex in the graph. So clearly the outer loop is contributing towards the O of V time complexity. Now the second thing what we need to calculate is the how many times this inner loop is running. So a lot of people will say that this particular inner loop is running E, that is capital E, that is the number of edges time. Okay, so the time complexity for this algorithm would be O of V into E. I've got this answer in a lot of interviews, right? That I've taken a lot of mock interviews, a lot of interviews that I've taken, but this is not correct. So if you'll see very closely, we are running the internal loop for each and every edge in the graph only once. Okay, so the internal loop was run. So we run the internal loop for the adjacent elements of 0, that was for 2 and 3. For this edge, this internal loop was run only once. Okay, and for this particular edge also, the internal loop ran only once. Okay, so if you'll see very closely that for each and every edge into this particular graph, the internal loop is running only once. So if you'll add all the runs of this particular loop across all the runs of the outer loop, it will totally add up to capital E, that is the number of edges. So the time complexity for this algorithm becomes O of V plus E, where V contributes towards the outer loop because I'm running this particular uh, um, uh, loop for each and every vertex, and capital E, that is the number of edges, contributes towards the sum of all the runs across all the iterations of the outer loop in the inner loop, right? So the time complexity is O of V plus E, capital E, where capital V is the number of vertices and capital E, just mind my writing, it's super bad, I know. So capital E represents the number of edges. Okay. So this is all about the topological sort. I'll quickly walk you through the code for this. Okay, so this is the code in C++ that has been written. Okay, so you can see this is the topological sort function. Okay, so firstly what we are doing is we are taking a vector which will store the in degree of each and every node, each and every vertex in this particular array. Again, I'm using a, adjacency list representation of a graph. So that is why it is like this, right? The graph is represented like this. We are not using adjacency matrix here, right? So again, once this loop will calculate the in degree of each and every vertex. So I'll go through for every vertex. I will, so let's say, uh, I'll just take 2 minutes to explain this. So let's say in adjacency list representation, we do something like this, right? So let's say there are two nodes, A and B, right? So there is A, B, and let's say this is C. So there is a edge from A to B, and there is a edge from C to B. So for A, there is no incoming. So sorry, for A, what are the edges which are joined to B? So I will put B here, right? Because A is joined to B. Like there's a directed edge from A to B. Similarly, there is a directed edge from C to B. So in C, I will insert B. So this is the adjacency list representation. And for B, there is nothing, right? So that B's list will be empty. So similarly, what we are doing here is we are going through each and every vertex, and I'm going through the each and every element in the list of that particular vertex, and I'm calculating the in degree, right? Again, we'll discuss this in detail, how to calculate in degree, like when we are discussing the topic in detail, right? Then we'll create a queue. Okay, and again we'll follow that particular algorithm. We'll try to find out what vertex have in degree equal to 0. Okay, all those vertex which have in degree equal to 0 would be pushed inside the queue, and then I'll try to run this particular loop in which I will pop out the first element. The running condition would be until the queue is empty, right? I will pop out the front element. Okay, I will print it, and I will try to go through all of adjacent elements, and will decrease the degree of all of its adjacent vertices, right? Now once the in degree of a particular vertex becomes 0, I will push it inside the queue, and this will do until the queue is not empty, right? So this is a basic implementation of this code. Okay, I like again, what is graph and all that we are going to discuss again in the course and all, right? So yeah, that is all from this particular topic. I'll again say you that like you might not be able to get what are graphs and all, right? Because in order to understand topological sort, you need to know graph and all. So when I start teaching my course from the very beginning, so I do not consider that you know what are graphs, what are arrays also, right? So we start from very basic. We just expect that you should know basic variables, constants, etc., right? Basic loops, if else, that you know, and that will be good to get started with this particular course, and that will help. This course will help you out in that. Again, if you want to like get access to the full course, if you want to learn along with me in 2 months period of time and polish your data structures and algorithm skills, you should go to this particular course page. Here you should see data DSA live for working professionals, and you can just explore that particular course. Everything is available here, right? What are the topics we are going to discuss in every week, and the next batch is starting from next weekend, that is 23rd of July, and I'll be the instructor for this particular course, and you can register at this particular page for this particular course, right? So okay, yeah, thanks all. Now I'll stop sharing my screen. I'll just quickly go to some of the comments, right? Stop screen.
Right. So thank you, Saurabh. That was really a very informative session. I'm sure people learned a lot from you. Just to tell the audience that this course is like you can register for this course. The link of this course will be in description. And please note that this course is on a 20% discount right now. So just grab the opportunity, and I'm sure you will learn a lot from this, because this session was quite, like a very simplified version of what actually the topic is. I mean, I perfectly understood it thanks to you, Saurabh. So I guess you can check the comments. There
Yeah.
are a few questions, and then we can go ahead.
Yeah. So there's a one question from Shrikant. Will this course help me in clearing companies like Urban Company and Walmart? Yeah. So this we just name it that like this is a FAANG level. Like we'll prepare you for FAANG. So it's just a reference, right? So again, whatever DSA which you'll learn in this course, that is going to help you in any company that you're sitting, right, which asks data structures and algorithm as a part of their interview process. So this is going to help you for any company that asks DSA, right? So you'll be able to do that. Like this particular course will help you for this for cracking the interviews at companies such as Urban Company and Walmart, right? Because DSA is asked everywhere, right, in every interviews, right? Somebody is asking, do you teach system design applications such as Tinder, right? So if you want to learn system design, we have courses available for that also in Geeks for Geeks. You can check to the live course section of Geeks for Geeks. There are multiple courses available for system design as well, right? I solve problem but can't solve at the rate GFC. This is a problem. Okay. Mm, I don't know, ma'am. Okay, so I don't find any other questions. So if you have any questions, you can just quickly pin. I'll take one last question. uh, in which type of questions can we use topological sort algorithm? I'll take that question. So let's say in a lot of interviews you are given, so I'll give an example. So this is from an Amazon interview. So I've seen, so they ask a question in a way that there is a program which needs to compile, and in that particular program there's multiple tasks which have dependencies on each other, right? So you have to tell whether you will be able to compile that particular program or not, right? So again, this is nothing, just a twisted manner of asking topological sort, right? So all those tasks are nothing, just vertices of a graph, and the dependency is just the edges between them. If you are able to make up a topological sort out of them, then it is, you can compile that particular program, otherwise not. So such kind of questions will be asked in interviews, right? Is being great at DSA enough for medium range product companies? Being great at DSA is enough for FAANG. So FAANG are not medium range product companies, right? So I'm not saying only DSA will take you everywhere, but DSA is, for at least for the fresh grads, DSA will take you everywhere. And for the experienced folks, DSA plays a significant role in your interview process. Is this course specific to SDE1? No, it is not specific to SDE1. In my previous courses, people at the experience level of tech lead, etc., have also enrolled, and they've got benefited from this particular course. Okay, so DSA is not a at something that as at SD1 something else will be asked, at SD2 something else will be asked. It is not that. Okay, so you can benefit if you are even SD1, SD2, anything. If you want to learn DSA for your interview preparation, then this is the course for you, right? Yeah. So I think that's it from my side, Dhwani. Thanks a lot for hosting me.
That's great, Saurabh. I'm sure people. I am sure everybody's questions were answered. If not, you can surely enroll in the course, and like you can directly get in touch with Saurabh over LinkedIn or via this course, and I'm sure he'll be more than happy to help you all. So I guess that's it for this session. Thank you so much, everyone, for joining us, and thank you so much, Saurabh, for such an interesting session. I'm sure a lot of people would love to, like get in direct touch with you. So
Guys, yeah, thank you guys. See you soon in the course, right? Bye bye.
bye bye. Take care.